Imagine a cryo chamber that spans an entire data center. One portion of it, let's say for whatever reason, is faulty. You have to drain all the vacuum, and to service that component, it takes days to actually do this. This is not a scalable approach. The scalable approach is to build smaller modular processors interconnected with a network. That's why we are investing in optical based and entanglement based technologies to build this quantum network.
Imagine a world where quantum computers seamlessly share entangled particles across data centers, solving problems beyond the reach of classical systems. This may be possible soon thanks to a groundbreaking quantum networking entanglement chip capable of generating 200 million entangled photon pairs per second, all at room temperature. Find out how Cisco is redefining networking again, doing everything from detecting eavesdroppers to laying the foundation for a quantum internet in this episode of the Post-Quantum World. I'm your host, Konstantinos Karagiannis. I lead quantum computing services at Protiviti, where we're helping companies prepare for the benefits and threats of this exploding field. I hope you'll join each episode as we explore the technology and business impacts of this post-quantum era. Our guests today are from a tiny little networking startup called Cisco. I think it'll catch on. I kid, of course. Reza Nejabati is the head of quantum research, and Ramana Kompella is a VP and head of Cisco research. Gentlemen, welcome to the show.
Thanks, Konstantinos, for welcoming us.
Thank you.
Yeah, I've been trying to get this going for a while. Some exciting news I wanted to talk about. And people hear Cisco and right away they think of networking, of course. So it should come as no surprise to listeners that we're going to be talking about quantum networking and some of the amazing things that are going to come as a result of that. So to start kind of with the most exciting immediate thing, you guys unveiled the quantum networking entanglement chip. It's a prototype developed with UC Santa Barbara. So maybe you can both jump in and sort of explain how it works, how it generates photon pairs, all that good stuff, just to give everyone an idea of what's so important about this.
Thanks for having us again. This is a chip that, as you mentioned, we jointly developed with expertise in University of Santa Barbara. There are many unique features about this chip that make it world first and world record breaking. One of them is that it's obviously the photonic integrated chip is very small, and for we use the material called 3.5 over compound semiconductor. That's basically create a kind of non-linearity effect that allows us for every photon that we inject to the chip, we get two lower photons that are entangled. And that's entangled photons. Also, they are in telecom frequency, means that they are compatible with existing installed fiber. Essentially, you can put it in the fiber infrastructure and move them around. Now, other features that are very unique for this chip is very high rate. It can achieve up to 200 million pair per second, which is very good because most of the quantum processes, as you know, are probabilistic in nature, and you have a rate, you increase your success. And also, it's very low power. Is less than 1 milliwatt, so that's make the chip is one of the unique and very functional and practical chip for quantum networking and also various application of quantum networking.
And it's room temperature operation, right?
That's correct. That's correct.
Yeah, because when people think quantum, they always think about refrigeration and all that complicated stuff. So room temperature is definitely important. So you already touched on the next thing I was going to ask you about, that it works with existing fiber optic infrastructure at standard telecom wavelengths, right? So how would this help develop and deploy new quantum networks? Do you envision any kind of like mixing, or still would this have to be a separate kind of network?
You can use your existing infrastructure. Again, depending on application. For most quantum application, let's say if you want to connect two quantum computers, you need a allocated dedicated fiber. Essentially, you cannot launch your quantum signal or entangled photon in a fiber that carries your classical internet traffic. But there are applications that we are working. They have some use cases for security, for example, or that they can potentially be used in coexistence with classical information. However, still you need to sacrifice for that the distance and your bandwidth of the fiber. Eventually, I think the most practical, reasonable approach to take. Use your existing fiber infrastructure and dedicate one dark fiber or one fiber for moving around your quantum network.
Yeah, just to add to Reza's comments, right? So I think the way I look at it is it really depends on the type of applications you want to build, right? So entanglement, generation, and distribution are really foundational to building a quantum network, right? So, but it really depends on how, and what type of application you want to run. For example, if you have a quantum algorithm that you want to distribute across multiple quantum processors, you need a quantum network that can distribute these entanglements, and you can do things like gate teleportation or qubit teleportation, right? So that you do partial computation in one processor, and you can actually then continue the processing elsewhere, and so on and so forth, right? Just like how distributed classical computing works. So that's one type of application. But to Reza's point, I think there are applications where you're really trying to figure out whether a particular fiber is actually being tampered with by an eavesdropper, in which, and this is a classical application, right? Your classical data is flowing over your traditional optical fiber, and you want to leverage the quantum properties to ascertain whether there is somebody on that fiber listening to the classical communications, in which case you're leveraging the quantum properties by mixing in quantum signals with classical signals, by carving out certain frequencies and stuff like that. So it's really, how what type of application you're focusing on that dictates how you leverage this quantum network. You just to sort of, paint the broader context here.
Interesting. So when you were just talking about the security eavesdropping thing, that's been a long known hope for QKD, right? This idea of the no cloning theorem, you can't pass on information. Are you saying that you might be able to just create sort of like a quantum heartbeat on a regular network to allow people to detect if a classical network is being eavesdropped upon? Is that what you're saying?
That's exactly right. QKD is obviously very well established. People are talking about distributing keys using quantum networks. But I think this is really just protecting against an eavesdropper listening to the classical communications, the standard Diffie-Hellman, or your key exchange protocols, right, that are happening in band, right? So to sort of avoid in order to circumvent the eavesdropper, right, that's basically listening to these key exchanges, you have the separate quantum network. That's where you're actually distributing your keys. That's the QKD part. But if you actually can detect the eavesdropper's presence, right, you don't need to worry about actually exchanging keys. This is a little bit of a low cost way of making sure your classical communications are actually secure against eavesdropper. And if you can actually imagine, if you can actually just integrate it across pretty much all fiber optics communications across the entire internet, the need for QKD will be reduced substantially. I mean, you may still want to do it as an additional layer of defense, but if you can just detect that there's an eavesdropper and stop your communication the moment there is an eavesdropper, right? That already means that you're not exchanging secrets that are prone to any kind of post-quantum attacks.
Okay, so you're talking about also then trying to detect the harvest now in the harvest now decrippulator attack scheme. And that might work for the wire. It's I guess I'd have to think about whether that would help if someone got access to like a port or something, like for spanning traffic like that. It might not help there, right? Because that would be the machine would sort of decouple and provide to the attacker what they want as if they were an authorized user, I guess, at that point. Interesting though to add that extra layer. Just it's almost like for free. So how do you envision the quantum internet going forward then? Before we dig into some of the other stuff that you're building, like I view it personally as its number one benefit would be entanglement between quantum computers, right? Like for me, that would be very important. Number two would be quantum sensors and keeping quantum sensors sort of in a quantum state as they interact with a quantum computer. To me, that seems like priority two. And then after that, it's kind of anything else, kind of anything else you could think of. So is that sort of how you're thinking about it too? Like this dedicated like entanglement network for machines and then filtering down in terms of complexity?
I would say yes, but I want to point out, as in Cisco, we try to be really pragmatic and realistic on what we can build, and that is practical and has a really impact and use in a relatively short term. So as you said, the quantum network, I think the flagship goal for us, if you like, is to connect quantum computers. And also, we are pragmatic about it. We want to build a network that works in a data center environment. We are not talking about a worldwide communication between quantum computers. We are talking about a controlled data center environment, which is short distance. That would be the first step that we are targeting. The same is for this, as you said, distributed sensing. We truly believe that network bring advantage with distributed sensing. Again, we are thinking about the short distances. For example, let's say in a medical scene that there is multiple sensors around specific machines that they need to connect together and to a small computing facility. That's give us an environment that really we can think how to build a network that can scale and work with reasonable capex and opex, if you like. And then after that, a lot of this technology gives us a footprint to build a repeater or a quantum repeater that allows us to go internet wide, if that's the case to be later. Yes.
And the quantum repeater would rely on things like memory
That's
and swapping, and it's essentially a quantum computer, right? I mean, it really is.
It's a small quantum computer, and we do all of them in a data center network. But that's a control environment. Once we know how to do it in a small environment, then we see how we can take it to the field for a repeater. Yes.
You can ramp it up. So this idea of connecting quantum computers together in a small, and like let's say inside of a data center. So we're talking relatively close together, right? A few feet apart or whatever is the idea. How does this compare to the current technologies being attempted to have chips be really connected close together? For example, IonQ's new roadmap is very heavy on this idea of the light sync technology connecting these new chips together with their electron gates. And I envision that as being like millimeters of separation, like almost nothing. So, how would this compare? Is this going to be not as fast if you have them in opposite sides of the room, or are there any kind of limitations like that? I just want to kind of set the stage for listeners a little bit of what it would look like if you were to connect these chips together.
The way I look at it is, much like, how you have classical infrastructure, right? You will have onboard networking, meaning, your sockets, like your processors on a motherboard, right? They are interconnected in some way, right? So there will be interconnects which will span short distances. And, maybe like there's proprietary technology out there which talks about how you can run traces in the backplane to sort of interconnect like servers within a rack, for example. Very different technology. You could actually go towards like cell-based technologies and other types of technologies to interconnect things within a rack. But eventually, I think, if you talk about communications across racks, or like, which span orders of like, meters, and maybe like few hundreds of meters, then I think like you need technologies which are not as proprietary, and you want to like, eventually, Ethernet has won. Okay. And Ethernet has won the interconnection battle in the classical networking space. I would envision like, an optical fiber based communication for quantum, building quantum networks will potentially win as you actually span larger distances. These proprietary interconnects will probably scale to a certain level, but to really truly get to that data center scale, which we are talking about, maybe interconnecting thousands, maybe a few hundreds to 1,000 to maybe even few tens of thousands of like quantum processors, you would really need a full scalable optical based entanglement based optical fiber based technologies to actually sort of like get to that scale. That would be my guess and prediction. Proprietary technologies will go only so far, and that's where I feel like, I think we are investing in. And the other thing I would also say is, imagine you have, okay, IonQ is one type of technology out there, but you also have these superconducting transform based technologies, like which are like, as you mentioned before, cryo chambers. Imagine if you were to actually have the interconnection, right, be part of the cryo chamber. Now you have to build a cryo chamber that spans an entire data center. Imagine one portion of it, like, let's say for whatever reason is faulty. You have to drain all the vacuum, and you have to service that component, and it takes days to actually do this. This is not a scalable approach. The scalable approach to actually doing this is to build smaller modular processors interconnected with a network which is basically outside of the cryo or any of the computing limitations or constraints, and that's actually the way to go. It is our belief that, that's why we are investing in optical based and entanglement based technologies to build this quantum network, which sort of builds the network outside of the computing regime. And that's actually, I think, the key to scalability.
Yeah, that's an excellent point. I'm glad that you brought that up.
Okay, because if I want to add to that, I mean, I was listening to before we come to this podcast, I was listening to your other podcast to see what I am gonna get the question. So you had a great podcast that I was discussing about the really we need to think about the quantum computer that make an impact and they do something useful, not just do another big factorial number that nobody knows what to do with them. I mean, so and
Oh,
that
people know
useful.
what to do with factoring a number, unfortunately.
Yeah.
They
Well,
definitely know what to do with that.
exactly. I
Yeah.
mean, well, not only just breaking the code, if you like. I mean, you want to you want to do something really useful and impactful. I mean, things that quantum can promise are things like a pharmaceutical and personal drug discovery. If you think about it, then we are thinking. Obviously, error correction are improving and everything with that. We are thinking realistically for something useful north of 10 million qubits. You want to also imagine that you don't want to people like old times come with their quantum circuit or algorithm in a queue in a big machine to wait. You want to also allow 1,000 scientists or pharmaceutical companies or pharmaceutical drug people, as example, to use it at the same time. So then the size really become a matter here, a number of the qubits, and then you have to see how much monolithically you want to go. If you think about the you mentioned a company that charge atoms or ion traps, then I don't know monolithically if you want to, even if you imagine the size of the laser control for a 10 million qubit, what would be, even is that possible or not, to put them around the same area or same vacuum chamber. If you think about the transmon one, the cryogenic one, I mean, you end up to creating a football pitch fridge to put your chip inside that and then operating that fridge as a football pitch size is going to create a lot of challenges and become not practical, not useful. Essentially, you need to create a way that you can scale them up, and that's the only network, that's the only possibility. The other thing that we see recently, especially from our theory team in literature, is coming up. If you have a network topology that you can reconfigure at the scale, then that creates a new opportunities for algorithm design, because the algorithm design are all considering the very fixed topological connection with the several constraints, how the qubits, if you like, teleport or connect with each other inside the chip or outside of a chip. But you allow the reconfigurability between them. That creates a new opportunity to do a more efficient algorithm, more different type of algorithm, if you like, for circuits.
So Cisco's announced a full quantum networking stack, including a distributed quantum computing compiler and the quantum network development kit, QNDK. Can you give us a sense of how these components will help enable sort of like a vendor agnostic integration across different technologies? For example, superconducting and trapped ion speaking to each other?
Yeah, I can comment on that, Konstantinos. Thanks for the question. So QNDK is our software stack for really controlling the entanglement-based quantum network. To your point, I think we definitely feel that there is value in really interconnecting different types of technologies, quantum computers that are based on trapped ions or superconducting. So for us, I mean, it's technology. We are sort of technology agnostic because we believe in interconnecting all types of networks. But QNDK itself is just basically the software stack that basically controls the various components like your quantum NIC, quantum switch, the entanglement source, and basically provides any server to any server connectivity in your data center, for example. And QNDK, the way we have designed, given that like not all components are still readily available, we have architected it in such a way that you can go from simulation to emulation to controlling real hardware. And we have applications that are basically like, some of which we have developed internally, like the distributed quantum compiler. We have some classical applications that we are looking at as well, but it's ideally extensible to, include other protocols and applications that can be built on top of the QNDK framework itself. So that's the way to think about it.
Yeah, like in the long term, it will enable possibly many different types to communicate, right?
Absolutely.
Modalities.
If I add to that, I mean, Connecting many quantum computers with our network is our aim and objective. But there is a software part, which is a QNDK and orchestrator, but there is also hardware part, which is how you connect the matter qubits, different modality of matter qubit. We have a transmon, charge atoms, natural atoms to our network. That is the basically network interface or a transduction, which we work to have a transduction capability for all major modality of the matter qubits to allow them to interface with our network.
Yeah, that's great. And I noticed that when it comes to all of this networking, you invested in Connect and Aliro Quantum. Both of these companies have been on the show before. I was just wondering what kind of like synergies you're establishing by investing in those companies right now. Are they bringing any unique hardware or software to this plan?
There is two companies, as you mentioned. QNet is one of them. QNet essentially works on the quantum memory. The main ultimate their objective is that, and quantum memory is for us is interesting. And also they work on an entanglement source, which has a very unique features. It is basically produce entangled photon that is in near IR regime, and also one photon is near IR, the other photon is in telecom. So that's together with the memory technology that they are developing creates a interesting hardware proposition if you want to interface quantum computing that they work at the neutral atom frequencies to our network. So essentially our aim for investing and working with QNet is that to see how their technology can basically help us to build the memory and also interface with the neutral atoms quantum computers. Aliro is also another company, but they are more on the simulation side of the software. And that's something that also we are closely looking at to them to see how they build a simulation platform for the various part of the quantum network. Yeah.
Okay. And before I shift the topic a little more to security, I just have one more question. So right now we have the 200 million pairs per second, right, of photons being created. What speed do you think you need to hit so this would become almost transparent to typical quantum modalities? Like what kind of impact would this be having on a gate right now?
At the moment, that's a good question. Still, we are doing the initial because that's the question is a little bit. It has a multiple angle to it. One of them is that okay, you have this 200 million photon is generating, then I need to use that to connect to the quantum computers. That's need a protocol, and that protocol also depends on the what type of the quantum computer, what technology quantum computer working. So to give you an example, some of the quantum computer they basically use the external trigger being these photons generated by our source to scatter back their communication qubits. The other they use other mechanisms to emit, so what we call it the emitter communication qubit in quantum computer or a scatter quantum communication qubit. And you may have also a combination of the both emitter and scatter. Now the question is that how you use this capability of the quantum computers with support of protocol at the end to do a swapping between them, and we need to consider the probabilistic nature of the entanglement source and also probabilistic nature of the way that these quantum computers emit their quantum communication qubits. That's all defined really what the rate we can use that we call it, as you said, transparent or everything works like a single quantum computer. At the moment, we are working on that. That's basically defined. We want to do if you like, a multi-objective optimization. How many communication qubit or interface your quantum computer needs, how many entanglement source you need, to connect the two quantum computer, and then more of them together. At the moment that we are at that stage, I don't have a definite answer to give you that.
Yeah, because when we're looking at a quantum computer, we're worried about like gate speeds, we're worried about fidelity. And obviously, this is going to be a whole new speed that gets introduced into the equation and a whole new fidelity because right now you're hovering around 99%, I believe, right?
That's correct.
Yeah. So it'll be interesting to see how this advances. So if we could switch gears a little to security, obviously security and Cisco have been sort of like hand to hand forever. It's been a major consideration. And we did talk earlier about adding this so-called like almost like quantum heartbeat. That's what I called it. I guess just this idea to detect man in the middle and things. How is Cisco approaching the entire PQC issue right now with integrating the new NIST finalists and that sort of thing?
So I think Konstantinos, that's a great question. I think PQC is, as you know, it standardized last year in August, and new FIPS have been issued.
Yep.
So I think across the board, pretty much all Cisco products have a roadmap towards integrating the latest PQC standards, and some which have been already announced, some which are underway, and that's a natural product journey because pretty much everybody is looking at migrating from TLS 1.2 to like 1.3 with MLChem, and this is
Hmm.
just basically natural product evolution, right? But I think I just want to comment that PQC alone is just one tool in the toolkit, right? So there is QKD, which we already alluded to and talked about, and then there is also the quantum heartbeat, as you call it, right? So these are all various
Hmm.
tools in the toolkit. So you really have to understand the full gamut of what information you're trying to secure and what is your threat vector here, right? Are you worried about people tapping into optical fibers in the middle of a forest somewhere and siphoning photons? Are you worried about some insider like hacking into a node? I mean, what type of like threat vectors are you really guarding against, right? So that's actually the critical part. And then the type of information that you're trying to protect, right? Is it like a secret like a Coke formula, for example, or like some financial data or some government secrets? Or are you talking about logs, for example, right? Like that machines are generating, which and the
Hmm.
longevity if it is not that important. So really you have to understand the importance of your data and your threat vector and figure out what the right tool is. That's the way I look at it. And I just want to also add that if you look at IPsec and MACsec, right? So we've actually integrated, or like we have this solution called the skip protocol, right? That allows us to partner with any QKD, external QKD devices to rotate the keys using quantum key distribution, right?
Yep.
So that part allows us to at least make our data plane devices like our iOS XR routers and so on and so forth be compliant with QKD if that particular customer chooses to deploy QKD, right? So we are approaching this in multiple fronts. And one of the last thing I just want to say is Outshift, our parent organization, is looking at new solutions around what we call it as PQC observability. In other words, how do we enable organizations to really understand their journey towards adopting PQC standards? Because, I mean, if you look at any enterprise, the digital footprint is just so enormous. How do you get that bird's eye view of like which hosts or like, which flows in your network are actually PQC compliant and which ones are not? And then marry that with your business priorities so you can actually say, well, these hosts are actually speaking old protocols which are not PQC compliant. So therefore, we have to invest in patching them. But it all starts with observability. So we are building observability solutions around how enterprises can understand what type of PQC compliance they have and prioritize their migration towards new PQC standards.
Yeah, that's music to my ears because the inventory part gets tricky. And then after you've taken an inventory, just tracking how things are going in real time is tricky, right? Like,
Exactly.
like are you actually doing the remediations? Are they working, et cetera, over time? So you're saying that you're working on something that might make that easier, either through like a dashboard interface or something like that?
Absolutely. So we are leveraging like eBPF and other things to and NetFlow, right? Essentially to collect flow information around what crypto ciphers are actually getting used for a given HTTPS connection, for example, and bubble that up to through the dashboards to sort of expose and say, hey, you know what, your host IP address X is talking to host IP address Y over like an unsafe PQC protocol, right? So therefore, like if you really think this X and Y need to be like speaking over a PQC compliant channel, consider upgrading these devices to speak new protocols, like adopt new ciphers, for example. So that's the kind of visibility that you need in order to prioritize your migration towards PQC standards.
Great. Yeah. And I have a feeling that in the next few years, as you hinted at, just about every device will be coming out with PQC already enabled. So it's to be expected. So one last quick thing before I let you guys go. I see there's also a quantum random number generator that you put out there. And I think that's great because I don't think we need to be tying up quantum computers to generate random numbers. This is very easily done with smaller devices. So if you just want to comment a little bit on the use case that you have for that.
So I want to mention that there are few quantum random number generator
Mm-hmm.
in, if you like, from startups and company available. The one that we have, it uses quantum vacuum noise, which is make it robust against the environmental effect like the electromagnetic and noise that are around the environment. Is very high rate. We can generate 100 gigabit per second random numbers. And also another unique features that relate to application and use cases of it is we can generate, or in our hardware natively, 3 different distribution of the random number: uniform, Gaussian, and Rayleigh. So that's expand the application target area significantly, because you can imagine application from security, from gaming, from or lottery, from the Monte Carlo simulation, from finance sector, and also from things like a wireless channel hopping. They all need a random number, but the quality of work depends on the quality of random number, which is with QRNG that we produce, and also they need a different distribution of random number. So our random number generator, because of this 3 distribution, can serve really a wide range of application that can benefit from it. Yeah.
Nice. Okay, so it's not really just for security the way you're pushing it.
Yeah, exactly.
Terrific. So with that, I want to thank you guys for joining. It'd be exciting to see how Cisco participates in this whole idea of the quantum networking and quantum internet, of course, going forward in the future. It's pretty hard to imagine separating Cisco from networking in any way, shape, or form. So it'll be fun to observe how this all goes on. So good luck with that, guys. Thanks.
Thanks, Konstantinos. I think these were excellent questions, and we had a lot of fun chatting about quantum future.
Thank you.
Thanks. That does it for this episode. Thanks to Reza Nejabati and Ramana Kompella for joining to discuss Cisco's quantum research. And thank you for listening. If you enjoyed the show, please subscribe to Protiviti's The Post-Quantum World and maybe leave a review to help others find us. Be sure to follow me on all socials at Constant Hacker. That's Constant with a K, Hacker. You'll find links there to what we're doing in quantum computing services at Protiviti. You can also DM me questions or suggestions for what you'd like to hear on the show. For more information on our quantum services, check out Protiviti.com or follow Protiviti Tech on X and LinkedIn. Until next time, be kind and stay quantum curious.